Container with most water. Imagine you're given an array that secretly encodes the largest container you can fill. Can you find it? Container with most water is a classic Pattern Mastery 100 problem, beloved by Phong interviewers because it tests for true insight into two-pointer patterns. Nearly half of all candidates stick to brute force and miss the elegant ON trick. If you can master this problem, you'll have a powerful template for dozens of similar questions. Let's crack it open together. Let's break down the problem. You're given an array of heights. Each height represents a vertical line on the x-axis. Pick any two lines. Together with the x-axis, they form a container. The goal? Find the pair that holds the most water. Area is calculated by the distance between lines times the shorter line's height. Let's assess our options. Brute force would check all ON squared pairs, much too slow for large arrays. The real trick? Notice that the only way to increase area is to move from the widest container to a narrower one, but hopefully with a taller line. That means we can use 2 pointers, starting at each end of the array, always moving the pointer pointing to the shorter line inward. This way, we never miss the optimal solution, and we do it in linear time. Here's the structure of our solution. Set 2 pointers, left at the start and right at the end of the array. While left is less than right, do the following. Calculate the area using this formula. The minimum of height at left and height at right, multiplied by the distance between them, which is right minus left. If this area is greater than the current maximum area, update the maximum. Then, move the pointer at the shorter line inward. Either increase left by 1, or decrease right by 1. Finally, return the maximum area found.
Let's try to implement it using solution 1. We begin by defining the solution class. This is the container for our method. Then we declare the max area method. It receives an array of line heights and must return the largest possible area of water the container can hold. Next, we set up 2 variables. Max keeps track of the largest area we have seen so far. N stores the length of the height array for convenience. After that, we start the outer loop where index I picks the left boundary of the container. This loop runs O of n times. Next, we begin the inner loop where index j chooses the right boundary. Together, these 2 loops check all possible pairs of lines. That makes the overall time complexity O of n squared. Inside the inner loop, we compute the area between lines I and j. The height of the container is limited by the shorter of the 2 lines, and the width is the distance between their indexes. Then we compare the newly computed area with our running maximum. If the new area is larger, we update max. That means we have found a better container. This continues until every pair of lines has been tested. Finally, after checking all pairs, we return max. That is the largest container area we found. And that's how this algorithm works. It tries every possible pair of lines. It keeps updating the best area whenever it finds a larger container. It explores all combinations in a simple, systematic way. Efficient, simple, and elegant. Check. This test case is for the container with most water problem. The height array contains the values 1, 8, 6, 2, 5, 4, 8, 3, 7. Each index is a position on the x-axis. Each value is the height at that position. We choose 2 lines to form the sides of a container. The amount of water it can hold is determined by 2 things. The shorter height, because that limits the water level, and the distance between the 2 indexes, which is the width. The maximum area comes from choosing a left line at index 1 with height 8, and a right line at index 8 with height 7. Now compute the area. The width is 8 minus 1, which equals 7. The effective height is the minimum of 8 and 7, which is 7. So the area is 7 times 7, which equals 49. No other pair of lines produces a larger area than 49. The output is 49, matching the expected 49. This confirms the solution correctly identifies the pair of lines forming the container with the maximum possible area. Now let's try another implement approach using solution 2. We begin by defining the solution class. This is the container for our optimized method. Then we declare the max area method. It receives an array of vertical line heights and returns the maximum container area. Next, we set up 2 pointers and a tracker. L starts at the leftmost line. R starts at the rightmost line. And max keeps track of the largest area we have found so far. This setup lets us start with the widest possible container and then narrow inward. After that, we begin a loop that continues as long as L is still left of R. Because each pointer only moves inward, this loop runs in O of n time. Inside the loop, we determine the height of the current container. The limiting height is always the shorter of the two lines. Next, we compute the area. Area equals height times width, and the width is the distance between R and L. Then we compare this area with our running maximum. If the new area is larger, we update max. After that, we decide which pointer to move. If the left height is smaller than the right height, we move the left pointer inward by 1. The reason is simple. The shorter side is the limiting wall. Keeping it while reducing width cannot create a larger area, so we try to replace it with a potentially taller line. Otherwise, the right height is smaller or equal, so we move the right pointer inward by 1. This keeps the strategy optimal. This continues until the pointers meet. Finally, we return max. That is the largest container area we discovered. And that's how this algorithm works. It starts with the widest possible container. Then it repeatedly moves the pointer on the shorter side inward to explore more promising shapes. It updates the maximum area along the way. Efficient, simple, and elegant. Check. This test is a minimal case for the container with most water problem. The height array contains 1 and 1. There are only 2 lines, so they automatically form the container. Now compute the area. The container height is the smaller of the 2 values. That is 1. The width is the distance between the 2 indexes. Index 1 minus index 0 equals 1. So the area is 1 times 1, which equals 1. There are no other pairs to consider. The output is 1, matching the expected one. This confirms the solution correctly handles the smallest valid configuration for this problem.
Let's have a quick recap. Breakdown recap. This problem challenges you to find 2 lines in an array of heights that, together with the x-axis, form the container that can hold the most water. The key is understanding that area depends on both the distance between the lines and the height of the shorter one. It's a geometry meets logic problem disguised as an array challenge. Assess recap. A brute force approach would compare every pair, but that's O(n squared), far too slow. The insight that changes everything is realizing that we can start with the widest possible container and only move inward where there's potential for a taller line. That's the power of the 2-pointer strategy. Maximum efficiency with 0 missed possibilities. Structure recap. We begin with 2 pointers, one at the start, one at the end. At each step, we calculate the area and record the maximum seen so far. Then, we move the pointer at the shorter line inward, since only a taller line can increase the area. The process continues until the 2 pointers meet. Implement recap. When the algorithm runs, it sweeps inward from both sides, evaluating each potential container in real time. The logic is simple yet clever. Always optimize by moving toward better heights while tracking the best result found so far. Every iteration gets us closer to the true maximum area. Check recap. Testing on our sample input confirmed it perfectly. The algorithm identified the optimal container formed between the heights 8 and 7, producing a maximum area of 49. The 2-pointer movement played out exactly as planned, validating both the logic and O(n) efficiency. The takeaway here is that efficiency often comes from strategy, not complexity. By understanding the problem's geometry and trusting the 2-pointer pattern, we turned a brute force challenge into a sleek linear time solution, a hallmark of top-tier problem solving.